Hey everyone, welcome back. Let's get started here. So I'm going to start off with a definition. So let's let L be a field, and then I want a subset. This is just a set here. So let's say and let X be a subset of L. So it's not a subring or a subfield or anything like that. Now, the subfield of L generated by X, and I'm going to underline this entire thing, but we're focusing on this generated, right? So what we have is a subset of our field, and then we want to look at the subfield generated by that subset. And so this is typical. It's the same definition as the subgroup generated by a set in group theory. So this is the intersection of all subfields of L that contain capital X, right? So just as the intersection of subgroups is a subgroup, the intersection of subfields is a subfield, and so we want the smallest, and here's a way to think of this, it's the smallest subfield of L that contains the set X. In fact, let's put that in parentheses. So it's the smallest subfield of L that contains X, in the sense that if you are a subfield that contains X, then you will contain this subfield. Right? And there's not special notation that we have for this. We're going to focus on a certain particular subfield generated by a particular subset, but there's not special notation for this general idea. We'll just say the subfield generated by. A couple of observations. The first one, the subfield generated by the empty set is the prime subfield. Remember, the prime subfield is the intersection of all subfields, and since all subfields contain the empty set, right, when you do the intersection of all subfields that contain the empty set, you'll get the prime subfield. The second observation, and this is the same, so same is true for the set containing 0 or the set containing 1, right? So if you look at the subfield generated by the set containing 0, you get the prime subfield. Same with the set containing 0, or set containing 1. And then the second observation, if X is not empty and X is not just the set containing 0, then the subfield generated by X, and I'm going to say this kind of vaguely, and then we'll make it more precisely. So then the subfield generated by X is the set of all and the set of all elements of L, all elements of L that can be built from the elements of X using field operations. So, for example, right, I mean, if you have, you don't need to write this down, but let me just give you an idea. So let's say that X consists of, let's say, just two elements, A and B for now. You don't need to write this down. So the idea is, okay, how are we going to create a field, or what will the elements of a field look like, the subfield generated by X, what will they look like? Well, it needs to be closed, and so it needs to contain A times B, and it needs to contain A plus B, and it needs to contain A divided by B, assuming B is not 0, and B divided by A. And so then you say, oh, okay, now it's got these elements. That means it needs to contain AB plus A, and AB plus B, and AB times A, and so on. And so by performing field operations, you start to build up this collection of objects, all of whom need to live within this set. And so by iterating this forever, essentially, right, what you end up with, that is what the elements of this subfield generated by X look like. I'm going to make that precise in just a second, but that's the idea you want to have in your head. You start off with some elements in the set, and you just start running field operations on them. And then you created more elements, and then you run the field operations on those, and you iterate that process, and that builds out, right, the subfield generated by your set X. Now, here's the important example. Let's say the main example, the one that we're going to work with. So, the main example corresponds to, well, let's say it like this. So if L over K is an extension, and A is a subset of L, then we're going to use this notation. So then K of A, or K parentheses A, is the subfield, or this denotes the subfield generated by a K union A. And you read this, when you see this, you say K adjoin A. So in some sense, what you're doing is you're starting off with the subfield K, and then you're saying, let's build this out, let's extend this field by adjoining some additional elements, right? And let's look at the subfield generated by that set. All right, so that's known as K adjoin A. And so what I want to do is make precise what the elements of K adjoin A are. And remember, when you're building the elements, right, thinking of, if you think about this set right here, right, you've got these building blocks, and you're going to just start iterating field operations to build it. So it's going to look, I mean, it looks not messy, but it's a big looking set. So let's consider the set, which I'll write as S sub A, right, where A is this set right here. And it's going to be the set of all possible products that you can form. So this will be, say, A1 times A2 dot 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 up to A sub, I got to use something besides K, how about A sub N, where each A sub I is either an element of A, or it can also be 1. Right, so look at all possible products of this form right here. Now, once we have this set, I can look at the span of this set right here. So let's say, and let V be the span of the set S sub A, and let's be clear who I mean here. It's the K span. So we're thinking of L as a vector space over K. So the scalars that we're going to use when we create this spanning set, when we create the span, right? We use the scalars K. So this is a subspace of the K vector space capital L. Now, okay, so let's state this as a theorem. K adjoin A is equal to, so what I want to do, I want to describe all the elements, and the elements are going to, this set V, or this subspace V, is going to allow us to describe them cleanly. So K adjoin A is equal to the set of all things of the form R times S inverse, where R is in V and S is in, well, we don't want to divide by 0, so it's in V minus 0. All right. The first thing you need to do, and I'm just going to leave this as an exercise, so check that this actually is a subfield of L. So we'll say check that the right-hand side, so check that the right-hand side is a subfield of okay, sorry, it's a subfield of L that contains, I mean, it's fairly clear, that contains K union A. It's basically rigged to make this sentence here true. And so what that tells us is, so, well, okay, we have a subfield that contains K union A, and K adjoin A is the smallest subfield that contains K union A. So that tells us that K adjoin A is contained in the right-hand side. So that gives us one of the inclusions. Now I need to show the other inclusion. So on the other hand, every element of V lives in K adjoin A. So it is contained in K adjoin A. Fine. Okay, so what does that mean? That means that all of the R's live in K adjoin A. And then, of course, all of the S inverses then also have to live in K adjoin A. And since K adjoin A is a field, it's closed under that multiplication. And so that tells us that the right-hand side has to live inside K adjoin A. So it follows that the right-hand side is contained in K adjoin A, and that completes the proof. Now, but here, an extension, so this is a definition now, so an extension L over K, I want to say, yeah, L over K, is simple if there exists a single element alpha in L such that L is equal to K join alpha. So if you can build L by adjoining a single element to K, then you say that this is a simple extension. Here's a quick example. The extension C over R is simple. Now, why is that? So the reason, you can check that C is equal to R adjoin I. And then another definition. All right, so this is more terminology that's connected with the whole idea of fields and field extensions. So let's let L over K be an extension, and let alpha be an L. Now, if there exists, and this definition is going to kind of give us a glimpse into the connection between polynomials and extensions. So if there exists some polynomial, say f in K bracket x, such that f of alpha is equal to 0. So if alpha is a root of some polynomial in K bracket x, then alpha is algebraic over K. If no such polynomial exists, then we say that alpha is transcendental over K. So if no such polynomial, polynomial exists, then alpha is transcendental over K. And the over K, I didn't underline the over K, but that part is important, right? You could have an element alpha, and depending on which K you're thinking about, the element may be algebraic, it may be transcendental, depending on the choice of K. Now, there is one special case. So a special case. Now let's just word it this way. So elements of C that are, and I'm going to just do this as a slash here, so algebraic slash transcendental over Q are, we refer to them as algebraic or transcendental numbers. So these are algebraic slash transcendental numbers. So if you're working with complex numbers, viewing C as an extension of Q, right? Or let's say this better, a complex number that is the root of a polynomial with rational coefficients is called an algebraic number. You don't say, if you don't say algebraic over blah, then by default you're talking about a complex number and it's algebraic over Q. Same thing with the transcendental part, right? So a complex number that is not the root of any rational polynomial, we call that a transcendental number. So for example, square root of 2, we know square root of 2 is irrational, but it turns out that it is algebraic. So square root of 2 in Q is algebraic. Why is that? Well, it's a root of x squared minus 2. That's irrational. And you know, I don't know why I put Q there. I should be putting a C there, right? The complex number square root of 2 is an algebraic number, and because square root of 2 is the root of this rational polynomial. There's some history that goes along with this. History that goes along with this notion of algebraic and transcendental. So the first one, it's due to Hermite. So Hermite in 1873, he proved that E is transcendental. So there is no rational polynomial that is transcendental. There's no rational polynomial for which E is a root. It's hard to prove, but it's true. The second one, this is due to Lindemann, and this is 1882. Pi is transcendental. I've never actually read the proofs of either of these two facts right here, but my understanding is that this one is quite a bit harder than this one. I guess I need to make a goal for myself to read these proofs. Okay, so we know that E is a transcendental, pi is transcendental. What about the sum? Transcendental, algebraic, unknown. So you would think, it seems like a reasonable question, right? Something to explore, but it's unknown. The sum of these two transcendental numbers is not known. It's not known whether it's transcendental or algebraic. You may or may not have heard of Hilbert's problems. So David Hilbert, he was probably the greatest mathematician of his time. And back in 1900, he gave a speech, an address in front of all of the great mathematicians of that time. And so this is in 1900 at the International Congress of Mathematics. He gives this speech in which he outlines 23 problems that he says are important for the future development of mathematics. And so these are known as the Hilbert problems. And so one of Hilbert's problems involves this idea of algebraic versus transcendental. And so this is Hilbert's 7th problem. Goes like this. If A is not equal to 0 or 1, and is algebraic. So if A not equal to 0, 1 is algebraic. And let's say B is irrational. So let's say, and B well, let's say B in B. I shouldn't have said irrational. I should have said is an algebraic number that's not rational. I guess. Well, okay. And B is irrational in the complex setting. So is algebraic. Is the power, so is A raised to the B algebraic? All right, so that was one of his questions that he asked, and this was solved. So the answer is yes, and it was solved, let's see, by a couple of different people. Gelfand in 1934, and right after that by Schneider in 1935. So these two solved it independently, weren't aware of the fact that the other one had actually solved it. One more, I mean, I don't know if this is really history, but yeah, kind of. It is the set of transcendental numbers. Uncountable. Transcendental numbers is uncountable. Which is, I mean, if you think of that just in the real line, it's very difficult to identify. It's very hard to find a transcendental number. I mean, E and pi, but in general, deciding whether you grab a number, or you're thinking about a number, to know whether it's transcendental or not, right, is difficult. But it turns out, even in the real line, right, there are lots and lots and lots of transcendental numbers. And this is just a cardinality argument, right? You know that the real numbers is uncountable, but the set of rational numbers is countable, and from that you can show that the set of algebraic numbers is countable, and that then then you can conclude that the set of transcendental numbers is uncountable. Oh, here's another example. E is algebraic over Q adjoin E. So we know that E is a transcendental number, right? But that means transcendental over Q. But it turns out that E, right? Well, if you allow your coefficients, right, to be in Q adjoin E, right, then E is a root of that polynomial right there. So that means it's algebraic over Q adjoin E. So now, given an extension, L over K, and some number L, or some element, some alpha in L. Remember this mapping, so we have the evaluation mapping. Last quarter when we did the evaluation, I did a phi sub alpha, but I'm going to change notation here. I'm going to use E sub alpha. Right, so we have the evaluation mapping E sub alpha. It goes from K bracket X to L, and how's it defined? Well, you take alpha and plug it into the polynomial, right? So, so given by E sub alpha of f equals f of alpha. It's easy to check that it's actually a homomorphism. Now, so there's two possibilities now. Alpha is either algebraic or transcendental over K. And those two situations give rise, or those two possibilities give rise to two totally different situations. So if alpha is transcendental, over K, okay, so what does that mean? It means that alpha is not the root of any polynomial. So no matter what you plug in here, if you plug a non-zero polynomial, you will not get 0. So what that tells us is that the kernel is trivial, right? So, so then the kernel of E sub alpha consists of just the 0 polynomial. If alpha is algebraic over K, then the kernel of E sub alpha, okay, so now it's going to be non-trivial, and the kernel is always an ideal, right? So what we have is a non-trivial ideal of K adjoint alpha. So then kernel of E adjoint, or sorry, E sub alpha is a non-trivial ideal of K bracket X. Fine, okay. Now what do we know? If K is a field, then K bracket X is a PID. Right, so since K bracket X is a principal ideal domain, that means that this ideal has a single generator. And if you remember back to the proof, when you're working or when you're showing that K bracket X, anytime you have a field, to show that K bracket X is a PID, you produce a generator for that ideal by saying, let's just take any non-zero polynomial of least degree. And it turns out that that will be a generator. So there's actually a whole bunch of generators for this ideal right here. And if we want, right, so there's a whole bunch, just take any non-zero polynomial of least degree that lives in here, and you'll be able to see that it generates. Now, amongst all those polynomials, there's exactly one that has 1 for the leading coefficient. Right? And remember, a polynomial that has 1 for a leading coefficient, that's called a monic polynomial. So since K bracket X is a PID, there exists a unique monic polynomial, monic, and I'm going to call it M sub alpha in K bracket X, such that the kernel of E sub alpha is equal to the ideal generated by M sub alpha. If you took my Math 482 class, I know in that class the notation was angle brackets for the ideal generated by some set. In this book they use parentheses. That's actually probably more typical to just use parentheses. And so we're going to work with that. When you see this around some element, right, that means ideal generated by. This polynomial has a name, so M sub alpha is the minimal polynomial of alpha. Now we need to be a little bit careful. It's really with respect to k's, right? So as you change k, the minimal polynomial is going to change. And so, I mean, technically, I should say, in fact, I'll write it down, is the minimal polynomial of alpha over k. Oftentimes, I mean, if no confusion arises, we're just going to say the words minimal polynomial of alpha. Right? But there will be times, I mean, to be precise, we really should specify that it's over k. And so more precisely, every once in a while, we may need to be more precise, in which case we might write m sub alpha comma k, the minimal polynomial of alpha with respect to k. Okay, so let's prove a theorem now. And this theorem is going to give us not only some insight about the minimal polynomial, m sub alpha, it's also going to give us a nice connection between the minimal polynomial and k adjoin alpha. So if we have m sub alpha, it'll tell us a connection between the minimal polynomial m sub alpha and the extension k adjoin alpha. So here we go. This is theorem 1.4. So let's let L over K be an extension. And let alpha in L be algebraic. Over K. Now, there's two parts to this theorem. The first part is that the minimal polynomial m sub alpha is irreducible. Over K. And then the second part is that the image of the evaluation map, E sub alpha, is equal to a K adjoin alpha, right? And so then by understanding what the elements of the image of E sub alpha look like, that's going to tell us what the elements of K adjoin alpha look like. Okay, so proof, first we'll do part A. Let's suppose, right, that m sub alpha factors. So suppose m sub alpha is equal to f times g for some f and g in k bracket x. One thing to notice, I mean, I kind of go back and forth, right? There's f of x and then there's f. In this book, they're a little bit more correct, right? In just writing the name of the function here. So we write m sub alpha, or let's say, what am I trying to say? We drop the reference to the variable in our polynomials here. So suppose the polynomial m sub alpha factors are the product of these two polynomials, f times g. Now, so then, what does that mean? It means that so 0 is equal to E sub alpha of m sub alpha, which is equal to, so I'm going to apply E sub alpha to this product, and because E sub alpha is a homomorphism, we get E sub alpha of f times E sub alpha of g. And so now in a field, right, where is this happening? This is happening in L, right? And so in L, we have a product of two elements equal to 0. That means that at least one of them has to be 0. So, so I guess let's say since L is a field, E sub alpha of f equals 0, or E sub alpha of g equals 0. Now, if, okay, so let's look at the case. If E sub alpha of f equals 0, then what does that mean? That means that, so then f is in the ideal generated by m sub alpha, right? M sub alpha, or the ideal generated by m sub alpha, is equal to the kernel. And so, oh, right, and so that means that if F is in the kernel, then F, right, has to live in this ideal. And so, what does that mean? It means that M sub alpha divides the polynomial F. So then, what do we have? We have F is equal to M sub alpha times H for some H in K bracket X. Okay, so now what do we have? So now F equals M sub alpha H, which is equal to FGH. And so now we can do cancellation because we're in an integral domain. And so 1 is equal to G times H. What does that tell us? It tells us that G is a unit. We could do a similar argument. So a similar argument holds. A similar argument applies for in the case that E sub alpha of G is equal to 0. Okay, so that shows us then that M sub alpha is irreducible, right? If M sub alpha factors, then one of them has to be a unit. And I just realized as I was going through here, I guess I could have done an alternate proof using a degree argument and the fact that M sub alpha has minimal degree, right? That would work also, right? If it factored, then these two would have to have degree strictly less than M sub alpha, or if they had degree strictly less than alpha, M sub alpha, we'd get a contradiction. But this argument does the job also. Okay, next, so for part B, okay, so I want to sort of set the stage here. So let's let Q from K bracket X to K bracket X mod the ideal generated by alpha. I want this just to be the natural projection. So be the projection. So that would be Q of F equals F plus the ideal generated by alpha. And what other mapping do I need? Let's let E sub alpha tilde. This is going to be from K bracket X mod ideal generated by M sub alpha. That's going to go to the image of E sub alpha. This is going to be the standard isomorphism that you get, right, when you apply the first isomorphism theorem. So this is going to be the standard isomorphism. Remember, this is the kernel of E sub alpha, and so this be the standard isomorphism. So what would that do? E sub alpha of F plus M sub alpha is equal to F of alpha. One more mapping that we need, so we'll say also let I, little I, from, I want to go from the image of E sub alpha tilde into L be the inclusion mapping. So there's a picture that goes along with this. So let me draw the diagram. It'll help us sort of keep our head straight. So let's see, I want to have a K bracket X and a, let's have L over here. Down below, we're going to have the quotient, so this will be a K bracket X mod ideal generated by M sub alpha. And then over here, I want to have image of E sub alpha. Okay, so this one right here, who's that one? That one, oh, that's E sub alpha. This one is our quotient. This one is E sub alpha hat. And then that's inclusion. All right, so we have this diagram right here. And what we want to see is that going across the top is exactly the same as going around the long way. And we just compute it. So so if f is in K bracket X, then when I do E alpha or E sub alpha tilde Q of F, let's see, that's going to be I E alpha tilde of F plus ideal generated by M alpha. That's going to be equal to I of okay, when I evaluate, or when I do E alpha tilde, that means evaluate at alpha, so that's I of F of alpha, which is F of alpha, and that is exactly equal to E sub alpha of F, right? So going around the long way, going this way, gives us exactly the same as if we come across the top. And what we say in this situation, if following the arrows in one direction matches following the arrows in the other direction, we say that the diagram commutes. So we'll say, so the diagram commutes. And commutative diagrams are they show up in algebra all the time. We'll see lots and lots of diagrams like this. And it just allows us to keep our head straight. Doing this is the same as this. Now, what we showed in part A is that M sub alpha is irreducible over K. So since M sub alpha is irreducible over K, what we know, we know that this quotient right here is a field. So we have that K bracket X mod ideal generated by M sub alpha is a field. Also then, okay, so this is a field, this is an isomorphism, this is a monomorphism, and so you can view this as a subfield of of L. And so, so let's say it like this also. Since E sub alpha tilde is an isomorphism, let's get this right here. The image of I E sub alpha tilde Q, which is exactly equal to the image of E sub alpha, is a subfield of capital L. Let me leave the diagram up there. Okay, So we know that the image of E sub alpha is a subfield of L. So now we know that if I apply, so E sub alpha of a constant polynomial little k, that's equal to k for all, oh, can I say this a little quicker? Oh, yeah, no, that's fine. For all little k in capital K, and E sub alpha of x is equal to alpha, right? Plugging in the polynomial x, the degree 1 polynomial, we get alpha. And so, what does that tell us? It tells us that k, together with alpha, live inside the image. So k union alpha is contained in the image of E sub alpha. What does that tell us? Well, k, so we can say therefore, k adjoin alpha is contained in image of E sub alpha, right? What is that, or why is that? Well, what we have is a field, I should say a subfield, that contains k union alpha. K adjoin alpha is the smallest subfield that contains k union alpha. Therefore, this side is contained in this side. And now I want to get the reverse inclusion. So on the other hand, so let's think about what elements of the image of E sub alpha look like. So image of E sub alpha is going to be, well, you take all polynomials in k bracket x and you plug alpha in. So that's going to look something like k0 plus k1 alpha plus k2 alpha squared plus dot 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 plus k sub n alpha sub n. Where the k sub i's are in capital K, and n is any integer greater than 0. But wait a minute now. Alpha lives in k adjoint alpha, k lives in k adjoint alpha, so all possible objects of this form live in k adjoint alpha, so this is clearly in k adjoint alpha. So now we have inclusion in the opposite direction. That completes the proof. And so this gives a nice description of the elements in k adjoint alpha. You can think of them as take any polynomial in k bracket x, plug in alpha, right? So they are linear combinations, if you like, of this form right here. And in fact, so that's the end of the proof, but let me just say it right here. So this gives a nice description of the elements of k adjoint alpha. Yeah, okay, so that's a good place to stop, and so we will see you next time.